Okay, what do we do next? We continue with homology of surfaces. Also, we follow the book, except for the fact that they emphasize groups, and we'll only get back to groups later in the end of April, and just do a few examples of groups. And so we stick with vector spaces. It is, frankly, complicated enough as it is. Just homology as a vector space is a lot of things to overcome. So anyway, so we are interested in one thing. So if M is a surface without boundary, we already have noticed certain patterns. We certainly know something about connectivity, and we want it to be compact, which is easily replaced with the word finite. So we are talking about cell complexes, so we are talking about then finitely many cells in that finite cell complex. Connected means that, well, we know now what connected means. It means that there will be H naught is equal to R. Incidentally, I think I should have discussed the opposite, the converse of the theorem that we discussed about the connectivity right here. This one. Where is that theorem? No. Path connected, remember the theorem that if the space is path connected, or rather the realization of the complex is path connected, then it is then the zero homology is R. But it actually the converse is also true. Something that we discussed once again last semester, that every vertex is homologous to every other vertex is equivalent to path connectivity of the realization. So, but that would be converse of our theory. Okay, so that's what we know about the homology of M, that H naught is R. Well, then there is H1, right? And we know that it varies a lot. So we have H1 could be 0, it could be R, could be R2, R squared rather. So, well, can you give me examples for each of these? A homology, a surface with these sphere. This is the sphere S2. The one with R. Do we have that? We other? I don't think we have that. For surfaces without boundary. With boundary, what is the surface with boundary? H1 is equal to R.
Movie screen?
What?
Movie screen?
Yes. Yes, well, I actually meant a cylinder, but maybe it's been also words. But they are with boundaries, so we can't really use it here. And for R2, it is the torus, and then you can go on and on with as many R's as you like. Just doing the connected sum, right? Wait a minute, what is the H1? 0, actually, no, it's a projective plane is 0. No, wait a minute. I forgot. It is hot in here. Okay, so well, let's put a question mark here. Anyway, because that's not really what we care about. We are here about we're interested in H2. Okay, so in other words, something that they have surfaces have in common rather than what they have different. So just like H0 is equal to R for a connected complex if it is a surface without boundary. What about H2? And the answer is basically the same, except now orientability matters. Okay, so H2 of the sphere is equal to R. That we did that. H2 of torus, I'm not sure we did it, but it is also equal to R. But if you take H2 of the Klein bottle, it is equal to 0. Okay, so that is the difference. In other words, we can actually classify or rather figure out the orientability of surfaces based entirely on the homology group. So suppose you have a cell complex which you know is a surface, and then all you know, as usual, you may have millions of those cells, and if you want to know whether it's orientable or not, turns out that all you have to do is to compute the second homology group. The non-orientable group surface was defined as the one that contains the Möbius band. Okay. Okay, so let's investigate this. So we are studying H2 of a surface. So what we have to look at is 2 cycles. 2 cycles versus 2 boundaries. Remember, homology is defined as the quotient of cycles over boundaries. What do we know about the boundaries? What?
And we're looking at surfaces without boundaries.
Right. Boundaries of a surface which happens to be a cell with cell complex of dimension 2. So what do we know about those boundaries of 2-dimensional boundaries? Well, 2-dimensional complex, what about 2-dimensional boundaries? What?
They're one chain?
No. You're thinking one boundaries. One-dimensional boundaries that are boundaries of 2 chains. Okay? But we are talking about this. So C2, C1, you know. So we're talking about this D of, but this is D of C3, right? That's what we're talking about. But what is C3 in a surface? What is C3 made of? No, it's not a trick question.
3 cells.
What?
3 chain and 3 cells.
3 chains, 3 cells, right? Okay. what do we know about three chains on the surface?
Dimension of three chain. We're talking about like,
Three chains made of, so C3 is made of three chains are made of three cells. What does a three cell look like?
So, solid
What?
solid
Q
cube.
cells.
It's like, it looks like a cube or tetrahedron or a ball, three-dimensional ball. So, on a surface, let's imagine a ball on the surface. Does surface how many balls, tetrahedron, and so on a surface contain?
Just one.
No. Less than one.
Zero.
Zero.
Made it easy.
Well, there are no three cells. There's then C3 is zero, and therefore certainly then we conclude that the boundaries are also there are no two boundaries.
Is this for any surface?
Yes,
Okay. Because.
it is a
what-
two-dimensional complex.
All surfaces?
Right. No three cells.
When we talk about two boundaries, we're talking about a boundary of.
Which the number refers to the dimension of the chain,
Okay.
not where it comes from. So two boundaries are boundaries of three
Okay.
chains.
So two boundaries, a boundary of a three chain.
Right.
Okay.
That's but this is boundary, three chain, two boundary. Okay. Okay, so that makes our life easier because now we only have to look at the cycles, because now it turns out that our homology group, two homology group, is equal to the cycle to the group of cycles. Right, because homology is Z2 over B2, B2 is 0, so all we care about is cycles. Okay, so we have to find, let's find all cycles. All two cycles in M. It seems complicated, but turns out, no, not really. So suppose C is a cycle, two cycle. Okay, then, well, by definition, DC is equal to 0. And what we know about DC is made of one cells, right? This is what we're talking about. So our C belongs to C2. It is a two cell, two chain. And now we want to find out, if we assume that it is a cycle, then what can we tell about? So it is made of one cells, okay? And the point here is that they all cancel. A bunch of one cells, and they all cancel. Well, this is where the fact that we're talking about surfaces comes into play. So it's not just the first fact about surfaces that there are no three cells. Okay, we just used it. The second fact about surfaces, what else do we need to know about surfaces? Remember, what is the difference between a surface and any other two-dimensional complex?
Locally R.
Right. So M is locally R, or not R, but rather R squared plane. Okay. What does it mean in terms of the cell complex? discussed this. About what does it mean about the cells of M?
I want to say something about being differentiable, but that's
No, no, we don't do any differentiability, no differentiation whatsoever.
I'm stuck on that.
Remember how the cells have to fit with each other.
Even in even pairs.
Say that again.
We're talking about in even pairs, like three of them can't.
Right, 3, what about 4?
4's fine.
No.
No. Okay. Just in 2s.
4, does this look like the surface?
Oh, okay. Yeah.
This looks like the surface. This does not. Okay, so your answer was correct, but incomplete. It has to be even correct, but more specifically,
In pairs.
they come in pairs. Yes. So more exactly, every edge is shared by exactly 2 faces. If this is our edge, these are the 2 faces, and there are no more. It cannot be 1 because that would create a boundary. It cannot be 3 or higher because that would not be R2 anymore. This is R2. I can pick any point here and it will be still homeomorphic to R2. Okay? Okay? So, okay, that helps. We're going to use it right here. You see, we want everything to cancel this thing. We want all of these one cells edges to cancel, right? So what does it mean? What?
Don't you have to have like some kind of orientation for them to cancel?
Well, yeah, we're not going to jump as far just yet. So suppose this is E, and E is in the boundary. Suppose so. E is in the boundary of say tau and sigma. Okay. Now, what can we say about what can you say about C? Then E has to cancel. Okay, so the E can possibly appear as far as C is concerned. E can appear in the boundary of tau or in the boundary of sigma only. Okay, which means that what does it mean for C? If it contains tau, then what?
Talking about it contains tau, and we don't know if it contains sigma yet?
Well, we don't know yet. Yeah, so
Alright, then E is the boundary.
no. Suppose C contains tau, and we want C. We assume that C is a cycle, so it means that all edges have to cancel. Okay. If C contains tau, then E is in the boundary of tau. Okay, so then E will be in the boundary of C, right?
Yeah.
So what does it tell you? E is in C, but E has to be canceled.
It's part of the cycle. We already know that.
Well, suppose C is equal to tau,
Okay.
right? Then its boundary will contain E.
Yeah.
Okay, is tau a cycle? The answer is sigma also has to be in C. Otherwise, there's no other way to cancel E. What tau C contains. Okay, since once again, the fact that number 2 above, every edge is shared by exactly 2 faces, then the only way to cancel E if both sigma and tau are parts of C. If only one of them is a part of C, then E will be standing there and will never disappear, and it means that DC is not 0. Okay? And then, yes, and then for even a chance to cancel, both of them have to be there. So that's the number 1 fact that we have established. Let me rewrite it. So let's rewrite it, that fact. So if DC contains E, then EC contains both sigma and tau. Okay?
What is E?
E is the edge.
Why did you put 2 lines?
What?
Why are there, did you just put 2 lines just to highlight?
Yeah, I'm sorry about that. Yeah, that's what I meant.
Oh, okay.
To emphasize that that's what we're looking at. Yeah, same story here. Okay, so it contains both tau and sigma, so that is a fact that we're going to use. But then it is then, we actually want if and only if. So we have then, if and only if, what would guarantee that tau and sigma, the presence of both tau and sigma cancels E, because that is not always the case. So let's suppose we consider this particular arrangement. So once again, this is E, this is tau, this is sigma. And suppose C is equal to tau plus, well, let's consider these orientations of tau and sigma. Probably should have a picture here, a bigger picture. E, tau, sigma, and suppose this is the orientation and that is the orientation. Okay, so C is tau plus sigma plus something else with these orientations. Okay, then let's compute the boundary. It will be what? Well, let's choose E going this way. Orientation of E going down. If you start computing the boundary, what do you get?
You'll be fine, right?
So it will be d tau plus d sigma, right? And so one d tau, what does it contain? It contains E, right? Plus some other stuff. And sigma also contains E plus other stuff, right? So assuming that there are other edges here we don't care about, I just put dot there, but E is with this orientation, this is tau, so E will appear exactly like that, going along. The orientations are compatible. The boundary of tau is E plus these boundaries, right? If you take sigma, then then the same thing happens, right? It goes counterclockwise in the exact direction as E, so E will appears again. Okay, so then the conclusion is then the end result is 2E plus some stuff. So what does it mean? They didn't cancel, and so the boundary is not zero. C is not a cycle. So then it means that, well, this is how it might not work out, even though we have satisfied this condition, right? C contains both sigma and tau, and yet there is no canceling. Why? Because the orientation is wrong.
So you get coefficient in front of E that's greater than 1. It means
Well, we
there's a
want-
fold.
We want, what do we want? We actually want either this turn into have minus here or that one have minus there, right?
We're talking about what we have. We have a fold, kind of a fold there, like two things. It's a pointed edge. E's a pointed edge.
What?
I was just talking about in that surface E will be like a pointed edge.
It is a directed edge, yes, that's what orientation is.
Right, like a fold, like it's folded at that.
What's the difference? What difference does it make?
It doesn't. I'm just saying
Oh.
in my mind, like because if it canceled, it wouldn't be a fold. It would be flat.
No, I can have exactly this picture, the exact same picture. And you remember we come up ourselves with orientations.
Yeah.
Orientation is entirely our choice, orientation of all the cells involved. So when I see a picture like over there, I assign orientations in this fashion, and suddenly nothing cancels out. Okay, so then to cancel, we have to actually is only assured by certain orientations that we have. So in other words, for it to cancel, the orientations of sigma and tau should be compatible in a certain way. And we know what it means exactly, right? So two cells that two cells. So two cells that share an edge. So then they should appear in C. That we are not talking about orientations of. I shouldn't have put it in here or here. The minus here. We're not talking about the orientation of the complex, because homology is independent of the orientations of the complex. We're talking about in which way tau and sigma should appear in E. That's what we're talking in C. That's what we're talking about. So then well, we certainly can fix the problem that we're having. We can fix it with appropriate choice of orientations, but ultimately we're talking about C. So in which way? So suppose the orientation of tau and sigma are given this orientation. Suppose this orientation is given. How do we fix the problem? Orientation, suppose, are already given. How do we make C a cycle? It's very simple. I'll put the minus here. So with these orientations, C is not a cycle. So let me add it here. So C is not a cycle. But let's not forget that C prime equal to tau minus sigma, and so on is, or might be. If that's the cycle that I define, then everything will work out. as far as E is concerned, it will get canceled, right? If I have a minus over here, minus, minus, and they cancel. Okay, so that's not a problem of orientation. We can't choose C. If orientation is not appropriate, then we at least could try to choose C appropriately. So then the problem actually lies elsewhere, and that is, certainly if we even make that choice, it doesn't mean that we have solved the problem. Because, so we are able to cancel tau sigma by just putting minus here. But what if something happens elsewhere? Okay, and that is fairly easy to imagine that you cannot just assign minus signs everywhere you want, because you may possibly have a circular operation, and as you say, these two don't cancel, so I give sigma minus sign, but then this one shares an edge with another one, and then I also have to change the sign of this, and then go on, and then I may come back to tau, and it turns out that I have to change the orientation of tau as well. So that doesn't really solve the problem. So it is easy to handle by, rather than looking at C, looking still at the surface itself. But before we do that, maybe okay. Let's continue with this one. Okay, so to cancel orientation, they should be compatible. So we have two cells, tau and sigma, that share an edge. Then we choose orientation. Then suppose there is a good orientation for tau and sigma. So we assume that orientations everywhere for all cells are already compatible. Okay, that share an edge. Then tau and sigma induce the same orientation on E. The opposite orientation, I'm sorry. Okay. So then, actually it looks better, because in this case, both of them are clockwise. Turns out, if both of them go clockwise, they will induce the same orientation, down. They will induce the opposite orientation. So tau will induce orientation down, and the sigma will induce orientation up. Okay, see how it turns out. Okay, and then whatever orientation of E is not important, because we choose orientation for sigma and tau, and then we say, well, let's choose that orientation for it doesn't matter what orientation of E is, because it will cancel. Then D tau plus sigma does not contain E. Right? Let me maybe clarify this. So, going clockwise, and it induces this orientation on E. And if I go also clockwise with the other one, then this is the orientation on E. Okay? If that's possible to do, then if this is possible, okay. If this is possible, because is it possible, that's the big question. But if it is, then here we are. Tau plus sigma does not contain E, right? So this is certainly possible if you look at one edge at a time, right? But what about, is it possible to carry out throughout? So yes, the answer is yes for E alone. Now, but what about all edges of M.